All the way out?
Yep.
I have green light.
Yeah, I just did that. I feel like this is a fire situation about to happen.
Oh, the whole hotel is right now. Yeah. Isn't that great?
The extinguisher.
Did it crap out?
Yep. I think it just did.
Which one did you? Where did you plug it in?
I haven't read the power strip.
Oh, this went right down to 0%.
This guy's dead. We're not using it.
You all can't see this, if you're following along. I'm Chris.
Where is this?
Research Science Director at Atredis Partners. Also a professional owl illustrator. If you're looking at the slides right now, I'm calling out the owl illustrator. And I did not realize that this is something not a lot of people are aware of. There's that kind of classic funny picture of how to draw an owl, and it says draw 2 circles, then draw the rest of the owl. I think in embedded work or working in general, we encounter a lot of owl problems, and I like to refer them as owl problems. So if I call out drawing an owl, or there's the owl, that's what I'm talking about. So kind of the driver behind this research is at Atredis, we don't have a sales team. The people who scope the work are the people who do the work. In this case, we had scoped some work on this embedded target we had not encountered yet. I had a little bit of research time before that actually occurred. So I decided to buy a dev kit, dig into it, and try to give the testing team a head start as far as what this device is and provide them some documentation.
What about the little one I had?
So the device is kind of mentioned in the name as the DA1469x from Renesas. According to their marketing materials, it is a microcontroller targeting small, low-power Bluetooth, low-energy systems like fitness trackers, watches, toys, home automation, and stuff like that. But at the end of the day, the things we really care about are the security things, like secure access, how is the debugging interface is turned off, SecureBoot, which is going to validate that application as it's started. And this one in particular, it provides this encrypted firmware, and that allows the developer to load an encrypted application from external flash onto the device. So on these devices, I'm kind of high level just covering this. Some people may be familiar, some not. So all these security controls are handled by the system's OTP or one-time programmable segment. It's a write-once area that allows the developer to kind of write those values in and control whether those are on or off. And once they're set, they are set. Ideally you want to turn off. Sorry, bear with me here.
You have part of it. Oh, I'm sorry. Okay.
It's just not going to display.
Sorry. So the developer is going to write into that area, configure those things, and do things like turn off JTAG, single wire debug, or some sort of a lot of times there's like a serial bootloader that allows you to reload if you need to. In this case, there's also the idea of these encryption keys. Those also get written to this one-time programmable area. There's actually room for 8 keys for the QSpy flash, some user keys, and then public keys that are used to do the validation. When those are loaded in, they are accessible by the crypto controller and referenced by an index into that.
How do you get it to?
So, again, mentioning the idea of this encrypted applications. In most embedded systems, controller, the application gets loaded onto embedded flash, which at the end of the day, it's going to be protected by disabling the debug interface, so like readback protection and stuff like that. In this case, the application is loaded from that external spy flash, and to defend against attackers who can physically access that, since it's not protected by the debug interface, readback protection, they chose to deploy encryption.
Huh?
You just hear what
In this case, it's operating in AES-CTR mode, and the reason that is that allows them to decrypt arbitrary blocks on the fly, instead of having to decrypt that whole application at runtime. And again, we touched on it before, the kind of the most important part in defending an embedded system is SecureBoot. SecureBoot, allows them to sign that application, and when it's started, that is checked against those public key values that are stored in the runtime programmable areas. And on this particular device, when SecureBoot is enabled, it cannot be disabled. And once it has been turned on, all those previous items are also enforced. So you have to be using encrypted applications, etc. So with all those things, how does someone audit? Do these things work? And that's going to be the job of BootROM. And that is a small block of code that's written to the device, and it's executed every time the device is powered on. It initializes that base state of the hardware and handles that transition to the user's application. Since the code that's physically part of the hardware, it's immutable and cannot be modified after that part leaves the factory. Mutable code kind of offers a strong defense against attacks since it can't be modified without access to specialized equipment, like focus ion beam or something like that. The downside is that any bugs that are identified can't be fixed, and it's going to require a brand new fabrication run. With the exception, if that vendor has some sort of small one-time programmable area that will allow them to patch and kind of, jump to other areas, a lot of times those are undocumented. I think the notable examples for the BootROM bug that most people are familiar with would be the iPhone, like Fine Rain, Checkmate. So getting to BootROM, sometimes it's accessible. You can just pull it out, it's not a big deal. Other times it is locked down, and actually, so to get a hold of it, you need bugs. In the case of this particular chip, the BootROM's mapped at a range that's in the document, the data sheet. And the easiest way to get a hold of that is connect a debugger to it, like JLink or OpenOCD or something like that, and just read the contents out of disk. And once you have that, you can actually, start that drawing the owl process, loading it through a decompiler or whatever your tool you like, and kind of figure out, okay, what is this doing in present? So there's a lot of challenges when dealing with something like a BootROM. 1 second, let's see if this works.
Yay.
We're back. If I can figure out how to do this. Are we good? All right,
Yeah.
perfect. That makes this much easier. So as the BootROM, that's hard-coded into the chip. There's not a whole lot of space on the chip to do that, so the code has to be dense. And that means, there's not room for common external libraries, debug statements, friendly strings, etc. And it can be scary or terrible feeling when you load something up into IDA or whatever tool you're using and you see no strings. Because a lot of times those are easy kind of cheats to figure out what's going on. So how to work around that. So while all those like debug strings and helpful details aren't there to use as a starting point, kind of the fact that the job of the BootROM is to initialize that hardware and pivot to the user application kind of makes things easier. By going over the data sheet, you can identify all those memory segments and registers and peripherals, and use that in your tool as a guide to identify functions that are referencing those. Segment creation and all that stuff we done manually or using scripting. Really the easiest way, if possible, is use an SVD file, which IDA actually has a loader built right in, which that wasn't always there. It works fairly well. The SVDs can be found online, off often like SDKs or IDE or some debugging tool will also ship with those, since they use them to kind of fill out those in the user interface as far as what registers there are and how those are configured. So once you have your segments loaded, that documentation into your tool, in this case we're using IDA, it's a lot easier to kind of work backwards from the hardware registers to the function they're accessing. And the kind of example that's shown here is the UART line controller, which is used to configure the enables boot. So kind of as noted before, the product header sections are completely open for modification. Talking through that, it seems, okay, that's great, it works. But see, the calculated matches the stored one. The size of the header is calculated using a value stored in that header. And most importantly, it's used to copy into a fixed length buffer some value. And that, calls out here, ends up in an overflow of the stack. And the last one here on the bottom was a distraction. You can loop that around to 0, but there actually was not a path to actually use that. It tried really hard to get an exploitable path in the payload, you have to fail the first CRC check with an invalid CRC in the primary. Next, the payload contains a backup header with a size larger than the target buffer that has a valid CRC for its size. The backup product header ends up clobbering the first target buffer, and you win. And everything's great, except it does not work like that. In order to pivot into the controlled stack, you need to successfully exit the function and go back to the boot flow. In the current state, it's just an infinite loop over and over again. The function will be exited by placing a valid CRC that is pre-computed for that new large primary header that's created at the correct offset from the primary. And then when it loops back, that primary passes, it will exit the function into the controlled stack. The other option is you can literally ground out the SPI flash and cause that to fail, and it will exit the function. And that was honestly the first thing I tried, since it was kind of painful to figure out how to get out programmatically. So this single payload kind of meets all of the requirements of the code execution. It contains a primary header with an invalid CRC, and an oversized backup header with a valid CRC, and a pre-computed CRC with a new updated primary header. By flagging that on there, on a device that has SecureBoot, but debugging still enabled, you can kind of walk through and see that, setting a breakpoint at that vulnerable call, you can see that at the point it's called, R1 holds hex with 3149, and that destination buffer is at R0. And then you have that before and after memory snapshot here, and that shows that original state return address get overwritten from the value in the previous. Halting right before that function exits shows that the execution's passed our control address, ending up in that infinite loop from that image. And kind of backing up to see, okay, where is this in the boot flow? This is before any SecureBoot functions occur. So it kind of invalidates that whole thing. Renesas did confirm and acknowledge that, and also this requires a brand new production run to fix, so this is a forever bug. Again, it's shown in that previous bug that unprotected configuration values are difficult to handle safely. The firmware security header provides writable values to configure BootROM for invalidating the signature as well as decryption of the application. The BootROM configures the hardware encryption engine with the values specified in here, setting the index to the correct key, writing the nonce value that is used for encryption of the application. The nonce actually ends up being the IV into that function. And again, we kind of called out that CTR mode is used because it allows decryption of arbitrary blocks, which facilitates execute in place. The downside is that none of this is authenticated, meaning the only way it can detect that something bad went wrong is crashing. This here is I looked at this, and this was the question I asked someone at work, because this did not seem plausible. Maybe you could get lucky and execute some uncontrollable code, but not an arbitrary data, no matter how many salt lamps or crystals I had on my desk. So thinking of the idea a bit more, I started looking at potential paths. The first blocks of the encrypted application are the ones that are going to matter, since they contain the initial address of the stack and the reset vector, which is the first function that gets called. The documentation shows that the QSpy flash memory space is pretty large and is mapped at 2 locations, which gave me some hope, but we had the question of could a modified nonce result in setting a reset vector to an address in that range? So instead of doing this on device slowly, it was just faster to simulate this process by creating a quick script that decrypts a block of an image using a no-nonsense key and seeing what fell out. I didn't expect much, but it didn't take long to get lots of hits that matches, so that was promising. The last step is does this actually work on the device? So using a device that is configured with the bug access, going through and setting it up and setting a breakpoint where that reset vector gets set, and determine does it match that value? Will this work? Can we jump to this place? This kind of shows that. That last bit on the bottom is just calling out. I wasted a lot of time here. If you're in the JLink and the T-bit does not match the address we're trying to jump to, it's super helpful, and it will just go ahead and fix that for you and allow it to go. So chasing my tail on why does this work when I'm debugging it, but not work when I actually try to do it outside of debugger. Hopefully you all won't run into that. So this looked feasible. One important part to cover is where does this occur in the boot diagram? And since it's after that validation, you need to ensure that validation passes, which ends up being fine since we're operating outside of that protected area. So anything after the application is fair game to place a payload. So with a known encryption configuration, it's easy to do this, but on a device, is this possible? And how do you detect if it's possible? And really the initial kind of idea here is you just fill it with nonce and monitor QSpy, and you can see if what you did worked or not. But again, nothing is easy. QSpy is a lot harder to monitor than I thought. My logic analyzer wasn't able to do that. The plugins I tried weren't successful. The other issue is these tend to use very, very tiny flash chips, and that means there's no place to expose a pin or pad and tap into that and monitor it. So you end up having to take it off and make crazy hacky things like this. So instead of trying to monitor in full, what about just one wire? And it's where I identified just monitoring the serial in. You can see there's a huge difference in a modified nonce that fails in boot loops versus the original. So that gives a good tell. The next step would be automating all this, and I let this run overnight. I got 241 captures, and it was actually the 154th. Looked nothing like the others. And going ahead and replaying that again, you can see that, yeah, that actually worked. It wasn't just a bug. So by confirming that, you have to figure out where it is, and it's kind of just chopping that smaller and smaller and smaller until it stops working, then coming back and adding until it works again. That'll tell you where that actually occurred. The other little trick I discovered is going back to the documentation. You can control what spy flash command is used. And here this ends up being, you can just set it to simplified mode and monitor it easily. And so here you can see use my monitor. That's the exact address I calculated. So now you have that tell. The third trick here is there's this idea of auto mode. If you're not allowed to write to the spy flash while it's in auto mode, which auto mode is required to do that on the applied encryption. And I'm being told that I'm out of time here. So at the end of the day, it comes down to writing this payload that reads that out and switches between auto and manual mode. It writes the decrypted value out using an invalid spy flash, then you can go through and scrape those logs out and actually get that decrypted payload. Again, when it says confirm this, it doesn't give you the key, but it, the things it's protecting are exposed. Again, this requires a new fabrication run. Real things that use this, Princess Cruise Lines use this for their access on their ships. Of course, people sell them on eBay. I have no idea why. So I bought some and put it apart, and they're not encrypted.